Hi, everybody.
I'm Cindy. So this is joint work with my colleagues Zhiki Bu and Wei-Ji Su from UPenn, and then Jason Kluzowski from Rutgers. So today I'm going to talk about statistical estimation of slope via approximate message passing. So a well-studied problem is that of linking a response variable y to a set of predictors that are chosen from some larger class of possible explanatory variables via a linear model, right? So standard linear model, we're going to assume here where y equals x beta plus z. Z is our noise, beta is our unknown signal, our unknown vector of regression coefficients, and throughout the talk we'll assume beta is sparse and my X matrix is short and wide. Right. So in this context, right, Lasso is a computationally efficient procedure with wide application, right? Despite sort of its wide use, Lasso doesn't actually come with a machinery through which we can make inferential statements about its solutions in finite samples. So slope is a generalization of Lasso that attempts to tackle that problem. So more precisely, right, when we think about the sparse regression problem, we're actually interested in support recovery. Like we'd like to find the coefficients of beta that are actually non-zero. And so in some sense, this reduces to a multiple hypothesis testing problem where we're testing the P null hypothesis that the coefficients of beta are exactly equal to 0 versus the two-sided alternatives. Right? So when P is large and we're interested in doing some sort of inference, this suggests that we should be making some correction because of the fact that we're doing a multiple hypothesis testing comparison, right? So I'm thinking something like Bonferroni or Benjamini-Hochberg that are common sort of multiple hypothesis testing corrections in the statistical literature. So slope was introduced as a generalization of Lasso that's wanted to privilege correct support recovery over minimization of prediction error in order that we could make confidence statements about the variables that it selects at finite samples. Okay, so what is slope? Well, we'll recall Lasso, right? Your Lasso estimate comes from a minimization of your sum of squared errors plus the L1 norm, and the amount of regularization or the amount of penalization that the Lasso does is controlled by the scalar lambda. So the idea of slope is to sort of break the monolithic L1 penalty of Lasso and instead consider a data-dependent penalty term. So one that regularizes the coefficients based on the magnitudes of the coefficients. Right? So the big idea here was that slope would be a way to sort of marry the advantages of the L1 penalty with the adaptivity that's inherent to multiple hypothesis testing correction procedures like Benjamini-Hochberg, which, it subjects the most significant p-values to more stringent thresholds. So the adaptivity of the slope norm gives slope a lot of nice statistical properties that aren't necessarily present for the Lasso, even though it's obviously the case that the Lasso is a special case of slope, right? If we take all of the lambdas to be the same, then we've dropped back to the Lasso procedure. Okay, so in this talk, I'd like to consider the algorithmic aspects of slope through the lens of approximate message passing, or what I'll call AMP, and then also show that the AMP theory can provide a powerful tool for statistical analysis of the slope. Okay, so Phil's talked a lot about AMP today, but so all I'll say is that AMP is a class of computationally efficient algorithms that have been studied for a broad range of statistical estimation problems, including compressed sensing and the Lasso. So as was mentioned earlier, right, so compared to our standard proximal gradient methods, AMP has an extra term in its residual step that sort of adjusts its iterations in a non-trivial way in order to give it good statistical properties, but also in order to improve the rates of convergence. So here I've just shown some empirical performance analysis of AMP in the case of slope when we're considering that our measurement matrix X is IID Gaussian. So I've plotted the optimization error and also the symmetric set difference of the supports when we're considering beta t, which is my slope, which is my AMP estimate at time t, against beta hat, which is the minimizer of my slope cost function. So in this case, AMP is in red. We've plotted the iterations at the bottom, and we're comparing to the proximal gradient descent, which is in black, and then an accelerated gradient descent in blue. So at least from this empirical evidence, it's suggesting that in this setting, AMP is outperforming these proximal methods in terms of rates of convergence. Okay, so the AMP algorithm for slope takes the following form. So at any iteration t, we update our estimate using the proximal operator associated with the sorted L1 norm that slope uses. And then once we have that estimate, we update our residual, which again is your standard residual plus a correction term, where in this case the correction term depends on the divergence of our proximal operator. So one thing to notice about the algorithm here is that these proximal operators use some threshold values, theta t, which is actually a vector of thresholds. So this is a non-increasing sequence of thresholds that I'll specify in a bit more detail later. But the idea is that it's through this vector of thresholds that we actually relate the AMP algorithm here to the slope cost function that we'd like to optimize. So in a sense, these theta t's are performing the regularization in the AMP algorithm, so they're related in a way to the vector of lambdas that actually give me my, my slope parameters. So one thing to note is that the proximal operator, so let's go back to the Lasso case, right? And if we consider the proximal operator for the L1 norm, then it turns out that this is separable, right? Separable meaning that the ith output value depends only on the ith input value. We know in the L1 norm case, this is Lasso. The proximal operator is our self-thresholding function. But when we look at the proximal operator for the sorted L1 norm, it's generally non-separable, right? So the ith output is going to depend on all of its input values. And at a high level, this coupling makes it much harder to analyze than it would be in a case that's separable. So the proximal operator becomes harder to analyze, and then therefore the associated AMP algorithm is also harder to analyze. So sort of due to the non-separability of the slope regularizer, it's difficult to apply AMP for slope directly. And for this reason, there's sort of a relative lack of existing work around AMP for slope. So in contrast, if we think about AMP for Lasso, right, the AMP theory has been rigorously applied, and it's shown both good empirical performance and nice theoretical properties. And then also, using the fact that AMP allows for asymptotically exact statistical characterization, and that we can show that AMP converges to the Lasso solution, then we have a tool for statistical analysis of Lasso. So in this work, we were hoping to, in some ways, try to fill the gap that exists for results about AMP for slope by giving a few theoretical guarantees here. So specifically, I'll show that AMP asymptotically solves the slope problem. This gives rise to an exact asymptotic characterization of slope by leveraging the statistical aspects of the AMP theory. And then this allows us to do fine-grained statistical analysis of slope. So at the end, I'll show an example of the kind of analysis that one can do with the AMP theory. So I'll also note that a recent paper by our colleagues Hu and Liu also gives an asymptotic characterization of the slope solution. So this is kind of my second point there, that matches ours but uses an entirely different proof method based on a Gaussian min-max theorem. And so, you know, while we get the same results, our AMP-based proof is more algorithmic in nature. So in some ways, I think it gives a more sort of concrete understanding of the finite sample behavior of slope as it relates to the asymptotic characterization. Okay, so throughout, we'll make some assumptions, namely the measurement matrix is assumed to be IID Gaussian, and I'm going to assume that the signal, the noise, and my thresholds are all drawn IID according to some distributions with some finite moment constraints. And that my undersampling ratio, so this is n over p, the dimensions of my measurement matrix, approaches a constant in the large system limit. Okay, so recall the AMP algorithm for slope. Right? We discussed the fact that it's through the choice of the threshold values, theta, that one ensures that AMP converges to the slope estimator. But before I can specify this relationship, I'll note an important fact of AMP, namely that the statistical properties of what I'm going to call the effective observation, so it's the term in red, which is the input to the prox operator. The statistical properties of this object are characterized by a deterministic recursion known as the state evolution. So specifically, the state evolution is a deterministic recursion that we're going to label as tau, and it actually describes the dynamics of the AMP iteration. So the state evolution depends on things like delta, which is the undersampling ratio of my measurement matrix, the prior distribution on my signal, and then also things like the signal-to-noise ratio of the problem. So it's been shown by Berthier et al. That even in the case of the non-separable prox operator, our effective observation is approximately equal in distribution to the true signal that we'd like to recover, plus independent Gaussian noise, where the variance of the noise is given by the state evolution. So this is a really important fact, and what it allows us to do is basically to note that then if we have that our state evolution is decreasing with t, so as the algorithm iterates, we're getting a more and more pure view of the signal through the effective observation. And so it turns out what we're actually able to show is that under certain conditions on the theta t sequence, that this is in fact true, that our state evolution will decrease and converge to a unique fixed point. Okay, so in terms of the calibration that we use to relate the theta t thresholds for AMP to the lambda thresholds for the slope algorithm, it takes the following form. We choose theta t to be proportional to tau t, which is the state evolution value, where the vector of the proportionality constants is a vector in the same direction as lambda, which is the thresholds for the slope. It's only scaled by a constant value that I'm not explicitly stating, but it depends on things like the sparsity in beta, the relative problem dimensions given by delta, and the signal-to-noise ratio. So then with this calibration, what we're able to show is that under some conditions on lambda, which is the distribution that I'm imagining my thresholds are initially chosen from, then the state evolution has a unique fixed point, and the state evolution sequence will converge monotonically to that fixed point from any initial conditions. So I'll just make a note that I'm saying that the conditions are on lambda, but in fact the conditions are on the distribution that this says that our alpha vector will come from, but in general they're kind of nasty to write out, so I did it. Okay, so now once we have this result about the state evolution, we're able to provide some theoretical guarantees about the AMP algorithm. So the first is that we can show that AMP provably solves slope in the sense that the L2 norm, or the L2 distance between the AMP estimate and the minimizer of the slope cost function goes to 0 and the large P and large T limit. So the proof of this, I'll say a few notes. It follows similarly to the proof in the Lasso case, but there are several challenges. So for example, unlike in the Lasso case, the slope solution may have more non-zeros than there are observations. So more than n non-zeros in the slope solution. So what this means is that even if we look at the slope cost function restricted to the support of the solution, it still may not be strongly convex. And so this causes some issues. We have to deal with this by sort of carefully developing new techniques that are tailored to the characteristics of the slope function. So for example, what we can say about the slope solution is that the number of unique non-zeros is upper bounded by the number of observations. So a consequence of that is that we get the slope estimator, beta hat, then inherits the performance guarantees from the AMP state evolution. So basically, we get an asymptotic characterization of the pseudo-Lipschitz loss between our slope estimate and the truth. So just a reminder, pseudo-Lipschitz loss is just a generalization of Lipschitz loss that includes like L1 and L2 loss. So then the result says that when we're considering pseudo-Lipschitz loss for large enough T and P, we can act as if our slope estimate is actually just the prox operator acting on the signal plus independent Gaussian noise. Right? So in other words, sort of the statistical characterization of the slope solution is now given by the AMP state evolution. So as a concrete example, we could take the L2 loss to be the pseudo-Lipschitz loss we're considering, and this gives an asymptotically exact characterization of the risk of the slope estimator, and that characterization is given by the fixed point of the AMP state evolution. Okay, so I'd like to give a quick example as to how this result can be used. So what I'm going to show is that slope dominates Lasso in terms of asymptotic trade-off between type 1 and type 2 errors. So as a note, this is still ongoing work, so I'll tell you what we know now, and though there is still some questions. Okay. So in the case of Lasso, there's a fundamental trade-off between the true positive proportion, which I'll call the TPP, and the false discovery proportion, the FDP, that's been rigorously characterized. So formally, my colleagues can actually exactly describe a curve that separates the TPP-FDP plane into an achievable region that Lasso can handle, and an unachievable region that no matter what the signal-to-noise ratio is, or no matter what the regularization parameter you can use, these are values that you'll never be able to achieve. So two such examples are plotted above. So basically, we've just divided the TPP-FDP plane, right? And the whole sort of favorable region is often not something that Lasso can achieve. So in other words, this is saying that it's impossible to drive both of the types of errors down to 0 simultaneously if you're using the Lasso. And so interestingly, for certain parameter settings, the TPP can actually be bounded away from 1. So this is like the plot up on the right. You can see that the TPP never is achieved above that line. And so this is actually something that's predicted by the Donahoe-Tanner phase transition. So what we can observe in the case of slope is that when there's no TPP bound, so if we're in sort of a delta epsilon region where this plane takes this form, then the trade-off curve is the same for slope as it is for Lasso. But when we're in the sort of plane where we have this sort of setting with the TPP being bounded, it turns out that slope doesn't suffer from the phase transition. So here I've plotted a black curve, which is actually the trade-off curve for Lasso. We simulated a number of random instances. The red points are Lasso solutions with various parameter values, and then the blue points are slope solutions with various parameter values. So we can see that slope can actually get over this bound on the TPP that exists for Lasso. So mathematically, there's some justification for what's happening here, right? So the idea is that in Lasso, as I mentioned earlier, it's going to select at most n, where n is the number of observations, of p non-zeros in the reconstructed signal. So this says the L0 norm of Lasso is going to be less than or equal to the number of observations. But for slope, the only thing that's bounded here by the number of observations is the number of unique non-zeros in the solution. And so therefore, in sort of an extreme case, you can come up with lambda values that you would find a signal that's completely dense, in which case, obviously, your TPP is going to equal 1. So you don't have the same sort of bound there. How would we prove this? Well, the big idea is to use the AMP analysis to characterize the trade-off curve exactly for slope, allowing us to construct a penalty sequence for any slope problem parameters that overcomes the Donahoe-Tanner phase transition. So I should note that my idea here is that when I say this, I mean that for any sort of delta epsilon pair, we can find a slope threshold sequence that actually gets us to any TPP that we're interested in. So as a sketch, because we don't have this quite done yet, the idea is that the AMP analysis gives us an asymptotic characterization of the slope solution in terms of the state evolution. This is the theory I showed earlier. This characterization allows us to study things like the sparsity, the FDP, and the TPP of the reconstructed signal. And then we can use the calibration and the state evolution to set constraints on the delta epsilon pair in terms of achievable FDP-TPP pairs, which are then translated into calculating the actual trade-off curve. Okay, so just in conclusion, so I presented an AMP algorithm for slope with its corresponding state evolution and calibration. I provided rigorous analysis of the state evolution and the feasibility regions for AMP. This allowed us to prove that AMP solves the slope problem asymptotically, which demonstrates exact asymptotic characterization of slope that can be used to look at statistical aspects of the slope problem. So thanks.